Hello, guys. It is official. I am very bored at home doing videos like this, and I officially miss being in school. Hopefully, a couple more weeks, we'll be back at it. Um, Mr. Vita introduced you guys to the chi-square test for goodness of fit, which is the first of three chi-square tests that we'll be looking at in Chapter 11. The chi-square test for goodness of fit was looking at the distribution of one categorical variable over one population. And the example that we kept using was the distribution of colors of M&Ms. Um, and then the population was M&Ms. So the variable was colors and the population was one population. In today's lesson, we'll be looking at the distribution of one categorical variable over two or more populations. It's called the chi-squared test for homogeneity. So back in chapter 10, we looked at two sample Z procedures for proportions, where we looked at two proportions and we compared them to one another. But if we want to look at more than two proportions, we have to start looking at a two-way table, which can organize multiple populations easily. So here is the example that we're going to be using a lot. Now, right now, I would like you to take out your calculator, and I would like you to just input this into a matrix before we get started, because we are going to be using matrices for this chi-square test. To input this into a matrix, I want to go into matrix, which is the blue letters above the x to the negative 1 on your calculator. So if you go into matrix, you can then edit a matrix, and you can edit matrix A. So we are going to input these numbers into matrix A. Matrix A should be a 3 by 3. We do not need the row and column totals. We only need the numbers on the inside, the interior of the matrix. Okay, so you're going to input a 3 by 3 matrix into matrix A, and I'll give you a minute to do that now before I continue. So this data is a researcher, and they suspect that the background music may affect the buying behaviors of customers. So they have three different treatments. The first treatment is that there is no music playing in the background. And then they analyzed right here what the customer chose to order. The next treatment was the French music playing in the background. And the final music was the Italian music playing in the background. And they calculated the number of people that ordered each type of food, French, Italian, or other, based on the type of music playing in the background. Okay, so this is now in matrix A, and we'll continue. We first want to analyze the conditional distribution of each entree ordered for each treatment, meaning I want to look at the conditional distribution of each treatment. So let's go back to our data here. Okay, looking at just the treatment of no music playing, I can see that 30 of the 84 people in this restaurant at this time chose French food. 11 of the 84 people chose Italian food, and 43 of the 84 people chose no food. No such other food, sorry. So if we go back to our question, it says calculate the conditional distribution. Well, for our first treatment, when no music was playing, you'll see 30 of the 84 people chose French food, 11 of the 84 chose Italian food, and 43 of the 84 chose other food. So it's about 36%, about 13%, and about 51%. Okay, so let's look at the next treatment. Our next treatment, if I go back to my data, was the French music. When French music was playing, 39 of the 75 people chose French food. 1 of the 75 people chose Italian food, and 35 of the 75 people chose other. So if we go back to our question, we can go to our next treatment, which is when a French accordion was playing, these are the percentage of people that chose each of these foods. Now we're using percentages because, again, we have different counts, right? In our first treatment, there was 84 people. In our next treatment, there was 75 people. So all of our treatments have a different a different denominator. So we have to look at percentages and not just counts. Okay, and then if we continue on to our last treatment, which is when the Italian music was playing, these are the percentage of people that chose French, Italian, and other food when the Italian string music was playing. Okay, and my goal is to compare these numbers. Before we can even get into our inference test, I want to compare them pictorially, meaning I want to create a graph. And here are my 3 graphs. You'll see the one all the way to the left is when no music was playing. The one in the middle is when French music was playing. And the one on the right is when Italian music was playing. And I just want to make some notes about these graphs. I can't make any strong conclusions because we haven't done an inference test yet, but I can definitely make notes about what I see. And the first thing that I notice is that the Italian entree chosen seems to really be affected by the music that's being played. If you look over on the right, when the Italian music is played, the Italian entree is chosen a lot. But in the middle, when the French music is playing, almost no one shows the Italian entree. So it seems like the music is really affecting the Italian entree. I'm also looking and I see that the French food seems pretty popular. Both the French here is pretty popular and here it's pretty popular. And so is the other foods. Like it looks like Italian food's not super popular unless Italian music is being played. So just looking at these graphs, I'm thinking, hey, maybe something's going on. Maybe the type of music does actually affect what a person orders when they are buying food. Okay, so let's continue to dive into this statistical analysis. Okay, ultimately what we're doing is multiple comparisons because we're looking at 3 populations now. Okay, we're looking at 3 treatments. So you have no music, French music, and Italian music. In order to do multiple comparisons, we're going to do an overall test to see if there is evidence that there is any differences amongst the parameters. So I'm not just comparing French to no music. I'm not just comparing Italian music to French music. I'm comparing all of the music at one time in an overall test. It's called the chi-squared test for homogeneity. If our chi-squared test for homogeneity shows that there is good evidence of a difference, I will then go ahead and do a follow-up analysis. A follow-up analysis will look specifically at the contributors of my chi-squared value. Okay? And the contributors will tell me specifically what parameters are different. Is it the Italian music? Is it the French music? So I can look more specifically at each of the contributors if my chi-squared test in general shows that there's a difference. Okay? So ultimately, I need to reject the null hypothesis in order to do a follow-up analysis. If I don't reject the null hypothesis, well, then we don't have significant evidence of any differences. Okay. So our null hypothesis is always that there's no difference. We're assuming that music, in this case, is not affecting the type of entree that we are choosing. Okay, so the null hypothesis in general is that there's no difference in the distribution of a categorical variable for several populations or treatments. Okay, so in our case, there is no difference in the distribution of entree chosen for all the different types of musics that are being played in the background. Okay, the alternative hypothesis is that there is a difference. Notice that the alternative is not talking about a specific category that's different. It's just saying in general there is a difference in the distribution of a categorical variable for several populations or treatments. Okay, so in our case there is a difference in the distribution of entree chosen in the music that's being played. Okay, so in order for us to look at the observed counts versus the expected counts, we need to actually calculate the expected values. For a chi-squared test for goodness of fit, you can do that using your list 1 and list 2. However, here we don't have list 1 and list 2, we have a matrix. So in order for us to find the expected counts, we need to do what's called the row total times the column total divided by the table total. So in this example, I'm finding the expected count of French entrees bought when no music was playing. So if we look at the observed count, 30 French entrees were bought when no music was playing. But the expected value would be 99 times 84 divided by 243. It's row total times column total over table total. So the expected number of French entrees chosen is 34.22. Okay, we got 30. Is it close? Yeah, it's close. Well, we can look at it later to see the contributor to the chi-squared value. How close was it actually? Okay. Okay, so it's row total times column total over table total. Now, a question that me and Mr. Vita got a lot in the chi-squared test for goodness of fit was, do we have to write down the expected values? If we go back to our normality check, and when we check the condition for normality, we always say that you can't refer to a graph without drawing the graph. So if you are referring to a histogram or referring to a normal probability plot, you have to draw the plot on your paper. Same thing here. If you are telling me that all of the expected values are bigger than 5, you need to write down the expected values somewhere on your paper. Okay, that goes for all 3 of these chi-squared tests. There is going to be a way to calculate the expected values on your calculator. It will do it for you. But right now, this is the only way we know how. Okay, and it's row total times column total over table total. And you don't have to show your calculations on your exams. You just have to write the expected values in a matrix on your exam and say, here are my expected values, and they are all bigger than 5. Okay, that's one of your conditions. So again, the expected counts is row total times column total over table total. And you can do that for each of the entrees chosen in our case. Okay, so each of the entrees. The other conditions, again, needs to be a randomized, well-designed experiment or a random sample. If we are sampling without replacement, do not forget to check your 10% rule. And then, of course, the large counts, like I said, they all have to be greater than 5. So, just as we do with the chi-squared test for goodness of fit, we want to compare the observed counts with the expected counts using the statistic chi-squared, which is just observed minus expected quantity squared divided by the expected, and then we add all of those values together. Okay, so in our two-way table, we have on the left side, you'll see that there is the observed counts, and on the right side, you'll see the expected counts. So if we were to do this by hand, we would do observed minus expected squared divided by the expected. So it would be 30 minus 34.22 quantity squared divided by 34.22. And that would be the contributor for the French entree chosen with no music playing. Okay, and I'll show you that here. So we have 30 minus 34.22 quantity squared divided by 34.22. So 0.52 is the contributor for that cell. Now, it doesn't seem very big. That's because 30 is pretty close to 34.22. Okay. Now, we would have to do that for every single cell and add them all together because the chi-squared value is the sum of all of its contributors. So we have to do that for every single value and add them all up, and you would get a chi-squared value of 18.28. Another question that we were getting is, what is a chi-squared value? A chi-squared value is just like a t-score, and it's just like a z-score. It is a standardized score, and ultimately it helps you find a p-value. A t-score just comes from a t-distribution. A z-score comes from a normal distribution. A chi-squared value or a chi-squared statistic just comes from a chi-squared distribution, which is just a different distribution than the first two we've looked at. It's a distribution that is skewed to the right, okay? And it varies depending on the degrees of freedom, okay? So we have a chi-squared value of 18.28. So our null hypothesis is that there is no difference between the true distributions of entrees ordered at this restaurant when the different music is playing. And then the alternative is that there is a difference in the distribution of entrees ordered at this restaurant when the different music is playing. We've already checked our conditions and we calculated our chi-squared value of 18.28. Okay. Now with that chi-squared value, you want to find a p-value. We can do this two ways. You can use a chi-squared table, which is what your book loves to do, but I strongly suggest against doing that. The other option is to use chi-squared CDF on your calculator. So if you go into distribution, DISTR above the vars, and you go down to chi-squared CDF. Chi-squared CDF is just like normal CDF. It's just like TCDF. It finds you the area under the curve. Okay. So chi-squared CDF, you have your lower and your upper. Now, when you're looking for a p-value, we're always looking for the right tail of a chi-squared and a chi-squared distribution. So our lower value is going to be 18.28 because that is our chi-squared value, and our upper value will be infinity. So I'm going to input a bunch of 99999s. Now, degrees of freedom. In chi-squared test for goodness of fit, you found degrees of freedom using, because you only had one variable and one population. It's different. For a chi-squared test for homogeneity, this is what you're doing right now, your degrees of freedom is going to be your columns minus 1 times your rows minus 1. So because our matrix is a 3 by 3, if you go 3 minus 1 times 3 minus 1, you get 4. So our degrees of freedom is 4. And when you paste that and hit enter, you would get a p-value of 0.001. Okay. Again, what this slide is showing you is how you would use a chi-squared table, table C. You do not want to use table C. Instead, you would rather use chi-squared CDF. Okay. Now, you do not need to do chi-squared CDF either, because your calculator can do this whole test for you as long as you have your observed counts in a matrix. And the first thing we did in this lesson was we input our observed values in a matrix. So right now in matrix A, you should have the observed values. If you go into stat and go over to test, and you go all the way down until you see chi-squared test, not chi-squared GOF, because that's the chi-squared goodness of fit test. This is a different inference test. Go to the chi-squared test. And when you hit it, it's going to ask you observed, expected, and that's it. The observed values are in matrix A. So make sure you have matrix A there. The expected values. You did not calculate the expected values. Well, you did. You just didn't put them in your calculator. The calculator will do it for you. What the calculator is asking for when it says expected is it's saying, hey, where do you want me to store the expected values that I'm going to calculate? So the calculator right now is going to store the expected values in matrix B. And when you hit calculate, you'll see it gives you a chi-squared value, a p-value, and degrees of freedom, which are the exact same values that you came up with by hand. Okay? Now you're probably like, wait a minute, where are my expected values? Well, if you go back into matrix, you'll now see that you have a matrix B, and it should be a 3 by 3. Matrix B is where your expected values are currently stored. If you hit enter on matrix B, you can see all of your expected values. You do not have to calculate them by hand. There will be times when you will have to calculate them on an exam for multiple choice questions. They might ask you for contributors, which you will probably need to calculate by hand for this type of test. So don't forget, it's row total times column total over table total. But in general, on a free response question, you will be able to use your calculator to find all of your expected values for you. Okay. All right, so we have a p-value. Our p-value is 0.001. Okay. And so that means that the probability, assuming that there's no difference in the true distribution of entrees ordered in a restaurant, when no music, French recording music, or Italian string music is played, there is a 0.0011 probability of observing a difference in the distribution of entrees ordered among the 3 treatment groups, as large or larger than the ones in this study. What the heck does this mean? Well, that p-value is very small. Very, very small. 0.001 is tiny. That's 0.1%. Because it's 0.1%, we are going to reject the null hypothesis, assuming that alpha is 0.05. Alpha could be 0.01 in this case, and we would still reject it. We have convincing evidence of a difference in the distribution of entrees ordered at the restaurant when the various music is playing. Okay? So there seems to be a difference between the music, the entree that's chosen, and the music that's being played. So what we're able to do now that we have rejected the null hypothesis, right? Step 1 was to do an overall test to look at all of the treatments at one time, to do multiple comparisons. So we have now done multiple comparisons. We have not decided which music and which entree is affected the most. We just know that there's something happening here, and there seems to be a difference over the various populations. So what we can do is now do a follow-up test. Okay, so a follow-up analysis. First, let's just do a quick summary. This is your chi-squared test for homogeneity. Okay, so this is your second chi-squared test. Chi-squared test for goodness of fit is number 1, and now this is a chi-squared test for homogeneity. Goodness of fit was one population and one variable. Homogeneity is multiple populations and one variable. In our case, the one variable was entree chosen. The multiple populations was the no music, the French music, and the Italian music. Okay, multiple treatments, multiple populations, but one variable. Okay, our null hypothesis that there's no difference. Our alternative is that there is a difference. Your calculator can find the chi-squared values for you. Your degrees of freedom are going to be the number of rows minus 1 times the number of columns minus 1. And don't forget that your 3 conditions to check are random, independent, and large counts. You need to write down your expected values in order to refer to your expected values. So write them down in the matrix so you can refer to them. Okay. Let's look at this example together. Random digit dialing telephone surveys used to exclude cell phone numbers. If the opinions of people who have only cell phones differ from those of people who have landline service, the poll results may not represent the entire population. the Pew Research Center interviewed separate random samples of cell-only and landline telephone users who were less than 30 years old. Here's what the Pew survey found about these people describe and how these people describe their political party affiliation. Now, reading this, how do I know I'm going to end up doing a chi-square test for homogeneity? Well, the key sentence here is that they took separate random samples. Because it took separate random samples, that means I have two random samples, and therefore I'm going to have two populations. So if I have multiple populations, I'm going to end up doing probably a chi-square test for homogeneity. And here I have multiple populations, and then my one variable is their political party affiliation. So again, multiple populations, cell phone and landline, and one variable, their political party affiliation. And therefore, I know I'm going to ultimately do a chi-squared test for homogeneity. This says, does this data provide convincing evidence at the alpha of 0.05 that the distribution of party affiliation differs in this under 30 cell-only and landline user populations? So let's first take a second and input this into our matrix. Again, we should go into matrix. We're going to edit the matrix A, and we're going to make it a 3 by 2. Okay, because we are looking at a different, not a 3 by 3 here. So 49, 47, 15. So I've input my values into my matrix. All right, now I'm going to stop there because I want to now go ahead and do my state plan do conclude. So in my statement, we want to perform a test where my null hypothesis is that there is no difference in the distribution of party affiliation in the under 30 cell-only and landline populations. So two populations. I have the cell-only and landline populations, and again, we're only looking at people under 30. So two populations. The one variable is the distribution of party affiliation. The alternative is that there is a difference in the distribution of party affiliation in the cell-only and landline populations. We're looking at an alpha level of 0.05. If the conditions are met, we will use a chi-square test for homogeneity. Homogeneity, again, is two or more populations. It is random because it comes from two independent random samples. Since we are sampling without replacement, we have to check our 10% rule. We are assuming that there are more than 960 cell-only users under the age of 30. And we are assuming that there are more than 1,040 landline users under the age of 30. Now, this problem was written a few years ago. At this point, I don't even know if the last part is a safe assumption because I don't own a landline, and I don't think I will ever own a landline, and no one I know owns a landline, and you guys will never own a landline. So maybe there aren't actually 1,040 landline users under the age of 30, but just to continue with the problem, we are going to make that assumption. Our large counts, we have to calculate the expected counts. Again, in order to calculate them, we can do it by hand. That's annoying. No one wants to do it by hand. Instead, we're going to let the calculator do it for us. So we're actually going to have to do the test in order to have the expected values. So if we go into stat, we go over to test, we go down to chi-squared test. Our observed values are in matrix A. Our expected values are going to be stored in matrix B. We can hit calculate. Now at this point, we're just going to ignore the actual test. I just want to see my expected values. So go ahead into matrix and look at matrix B because that's where my expected values are stored. And this is what you should see. Those are my expected values in my matrix. And because all of them are bigger than 5, the large counts condition is upheld, and I can continue with my chi-square test for homogeneity. Now we can go ahead and do the test again, because in our do section, we need our chi-squared statistic and our p-value. and our degrees of freedom. Our degrees of freedom here is 2, because it's 2 minus 1 times 2 minus 1, 3 minus 1 times 2 minus 1, sorry, to give you 2. And our p-value is 0.1999, and our chi-squared value is about 3.22. Those were all the values that were given to us when we did our chi-squared test in our calculator. That p-value is pretty large. So because our p-value is bigger than our alpha, we are going to fail to reject the null hypothesis. There is not convincing evidence that the distribution of party affiliation differs in the under 30 cell-only and landline user populations. Okay, all that means is that we are not going to do a follow-up analysis because we didn't see an overall difference. So there's no reason to do a follow-up analysis. Okay. Again, if we're looking at a follow-up analysis, we are looking at the biggest contributor. What are my biggest contributors to my chi-squared value? Now, in this test, there is not a way to see your contributors like there is in a goodness of fit test, right? So your calculator stored the contributors for goodness of fit. It does not store contributors for the homogeneity test because it's a matrix. So oftentimes, if we are doing a follow-up analysis, the question will probably give you a table that shows you the contributors. And then your task would be to just decide, what's the largest, and then just talk about it. Say, hey, we rejected the null, so something was happening. And then when you do your follow-up analysis, you can say that the biggest contributor is this row right here or this cell right here. And that's probably what's causing the overall trend to be different. Okay, so here is an example of that. Okay, so we're going back to our test with the music and the entree chosen. And you'll see in the bottom right corner, they give you, like I said, all the observed counts, and then right below them is the expected counts. And then the third number in each of those cells is the chi-squared contributor. Okay, so you look at some of them are very small, like this one is 0, this one is 0.5. Some of them are very big, 2.3, 7.67, 6.404. Okay, and your task is to do a follow-up analysis, because in this chi-square test we did reject the null hypothesis. We should go ahead and do a follow-up analysis. And looking at this, you can see that there are 2 really big contributors. There are those 2 right there. Okay, those the French music playing and the Italian music playing, and it's looking at the Italian entree chosen. So you can see, looking at the output, we see that there is a conclusion we can kind of come to, and that the orders of the Italian entree are strongly affected by the French and Italian music, which is kind of what we looked at in the very beginning, right? In the very beginning, we analyzed the graphs, right? And when I analyzed the graphs, I said, wow, Italian entrees seem to be affected a lot by music. And the other entrees, yeah, they changed a little bit, but the Italian entree changed the most. That's when I first noticed. But now we have statistical analysis to confirm what we originally thought just by looking at a picture, right? Because a picture doesn't tell us the whole story, but it tells us some of the story. And now we have this inference test that says, hey, Italian entrees are definitely affected by Italian music and French music. In fact, those 2 cells make up almost 77% of my chi-squared value. That's my follow-up analysis. Okay, so a quick summary. We added a second chi-squared test. So the first one is the goodness of fit, and it was 1 categorical variable and 1 population, meaning that we're only taking 1 sample. And the example that we did was the distribution of colors of M&Ms. So the variable was color and the population was M&Ms. Homogeneity is one variable in multiple populations or multiple treatments. So the two examples that we did, the one variable was the entree chosen, and the multiple treatments or populations was the music playing in the background. And the second example we did was the one variable was political party affiliation, and the multiple treatments or multiple populations was the landline versus cell phone users, right? So I did two examples. One where it was an experiment with treatments, and one where it was a sample. Okay, we were sampling. If I'm taking multiple samples, that means I'm looking at multiple populations. Okay, this is the end of the chi-square test for homogeneity. We will have one more chi-square test. It's called a chi-square test for association or independence, and we will look at that later this week. Okay. Once again, guys, I'm bored. I hope you guys are home safe. Enjoy your time at home. Don't leave unless you really have to. And keep an eye out for an update on the AP exams, as College Board has been changing their policy over the last few weeks about how and when the test will be given. So I'll continue to update you guys.